Alrighty, type 2. You'll notice, I mean, even right from the start, these types aren't as complicated as the ones in KAQ in Unit 2, so I haven't written much. So type 2 is finding solubility from KSP. So what you're going to want to do is write the dissolving equilibrium, write the KSP expression, and look up KSP. And then you're going to use mole-to-mole ratios to set up unknown concentrations of the ions and solve for the unknown concentrations of the ions. I'll show you what I mean. So this says calculate the molar solubility and solubility in grams per liter. So molar solubility and solubility in grams per liter of silver chloride. So the first thing I'm going to do is just write the dissolving equilibrium. So silver chloride solid is going to dissociate into silver ions and chloride ions. And this is an equilibrium, so it goes both ways. And that's all the information they're going to give you. And what we're going to want to find is the moles per liter solubility of silver chloride and the grams per liter solubility of the silver chloride. Now we know that KSP for this dissociation is going to be the silver ions times the chloride ions. Let's start nice and simple. Okay, so where are we going to go from here? Well, we're going to look up KSP. So we're going to use our data package, and we're going to say that the KSP for silver chloride is going to be down here. Silver chloride is going to be 1.8 times 10 to the negative 10. 1.8 times 10 to the negative 10. But what's the problem with this equation, right? If I leave it like this, I have 1.8 times 10 to the negative 10 is equal to silver times chloride. I have two unknowns. So what we're going to do is we're going to use our mole-to-mole ratios to set up our unknown concentrations of the ions. In other words, we're going to have X moles per liter, X moles per liter, and X moles per liter. If there was any coefficients, we would have two X's, and so obviously that's what the next example is going to show. So instead of having two unknowns, we're going to write our unknowns in terms of X using our mole-to-mole ratios. So then I'm going to say 1.8 times 10 to the negative 10 is equal to X times X, or just X squared. So that if I wanted to solve for X, I could just take the square root of both sides. So X is going to equal the square root of 1.8 times 10 to the negative 10. Which to 2 sig figs, because I'm at my answer, is 1 point. Now I'm at my answer, but I'm not. So I'm going to keep this in my calculator. So 1.3416 times 10 to the negative 5. But my answer is going to be that this is X. This is the concentration in moles per liter. And since this is all a 1-to-1 ratio, then the concentration of silver chloride, or the molar solubility of silver chloride, is going to be to 2 sig figs 1.3 times 10 to the negative 5 molar. But now I need to change this to grams per liter. So what I'm going to do is say that this answer is moles per liter, and I'm going to multiply it by 1 mole of silver chloride. Well, maybe I'll show that. Sorry, I can show it here, but I just want to show you because in the next example where it's not necessarily always a 1-to-1, actually you're always solving for X, so it is always the 1. Sorry, I'm just rambling. First time through the videos, I'm talking to myself. Welcome to it. So when you get this answer, this is kind of an interesting thing to think of. You know, I had this brain process where I was like, ooh, could I always change this guy? Well, if this was a 2x and this was a 3x, it's always going to be a 1 to 2 to 3 ratio. So this answer that you get for X is always going to be your molar solubility of your solid. Right? So you could actually always convert this. I just had this fear that, you know, if the ratios change, that would change, but it won't. I just had to think that through. So this is 1 mole, which is always going to be 1 mole breaking down. So we're going to convert this into grams per liter. So we know that 1 mole of the silver chloride weighs what? Well, silver chloride is made up of 1 silver, which is 107.9, and 1 chloride, which is 35.45, to give us a molar mass of 143.35 grams per mole. Okay, so I'm going to put in here 143.35, and then I'm going to plug this into my calculator. So I've got my answer recorded, and I'm going to multiply by 143.35, which is going to give me 0.001923 ... grams per liter. And so I'm going to put that my solubility in grams per liter to 2 sig figs is 1.9 times 10 to the negative 3 grams per liter. Okay, so now what we're going to do is we're going to do this exact same example again, but I'm going to change the subscripts. So I'm going to make it so that it's not a 1-to-1 ratio, but the process is going to be the same. So what are we going to do first? Well, we're going to write the dissolving or the dissociation of silver carbonate. So silver carbonate is going to dissociate into 2 silver ions and a carbonate ion. So to write the KSP, KSP is going to be the concentration of silver squared times the concentration of carbonate. Then we're going to go to our sheet and we're going to look up the KSP for silver carbonate. So silver carbonate is 8.5 times 10 to the negative 12. And then we're going to figure out what to put in for silver and carbonate. So my molar ratio is going to be X to 2X to X. So in for silver, I'm going to put 2X, and that's going to get squared. And in for carbonate, I'm going to put an X. So this is going to be 8.5 times 10 to the negative 12 is equal to 4x squared times x, which is 4x cubed. Then you're simply going to just solve for x. So you're going to divide by 4. So I'm going to do 8.5 times 10 to the negative 12 divided by 4. And then I'm going to take the cubed root of that answer. So I'm going to take the cubed root of that answer, and I'm going to get 0.000128564. Now for this one, all they wanted to know was molar solubility, so I'm going to say that the molar solubility of Ag2CO3 is equal to 1.3 times 10 to the negative 4 moles per liter, or molar. Awesome. All right, one more. So this one has a little bit of an extension on it. This one says, what are the concentration of magnesium and hydroxide in a saturated solution, meaning at equilibrium, of magnesium hydroxide? So again, I'm going to start by writing the dissociation of magnesium hydroxide into magnesium ions and 2 hydroxide ions. These start to get a little repetitive, which is great. I can even know right away that this is going to be my molar ratio. My KSP expression is going to be the magnesium times the hydroxide squared. So then I have to look up the KSP. So magnesium is M, hydroxide is going to be 5.6 times 10 to the negative 12. And that's going to equal X, whoops, I forgot my squared, times 2X squared, which is again going to give me 5.6 times 10 to the negative 12 is going to equal 4x cubed. So then to solve for x, I'm going to take that 5.6 times 10 to the negative 12. I'm going to divide by 4, and then I'm going to take the cubed root of that answer. That is going to give me to well, no, we're not at our final answer yet. So I'm going to get 0.000111868, so that I can say that the concentration of magnesium is just that. It is 1 point to 2 sig figs, 1.1 times 10 to the negative 4. And then the concentration of hydroxide is going to equal 2 times the answer. So I'm going to take that and times it by 2, which is going to give me 2.2 times 10 to the negative 4 moles per liter, or molarity. All right, hopefully that felt good. That is type 2.